Okay, some remarks. Number one, I said last time how to crack RSA. Actually, you will be able to do it if you get the secret key D. Now, if we go back to what RSA is. Yeah, we will be able to decrypt if the private key is D. Here is the D. And well, there are other parts of information that's also regarded as the private key. That's not just D, right? Not just D. And there's P and Q. However, the only essential part to for decryption is the D, which is the 23 here, and then this P and Q, they are part of the secret key that can be used to derive the D. Okay. So the observation is you really don't need this P and Q, those P and Q, in order to decrypt. Yeah, because the decryption you only take D. So is it possible to find D directly without knowing P and Q? That could be possible, but we don't know. We don't know yet. So theoretically, it's still possible to invert RSA without knowing P and Q. Okay, without factorizing N. However, so far, the best way known to invert the RSA is factorization. So far, we don't know whether there's any method, when any algorithm exists that can be applied directly to calculate D. So the best running time for the proved algorithm is this algorithm to, actually this may not be the best so far. This is just a way of inverting, of factorization. But every year there's still some improvement. So maybe this is a little outdated because I actually haven't updated this for a while because I'm not a mathematician. In practice, we may consider others. So there may be others way, but their performance cannot be guaranteed. There are usually although there are many other algorithms that can be used to calculate to do factorization. Most of them they only work on the smaller cases, on a subset of integers. For example, like there's some integer that has to be of a special format in order to be factorized. Okay. Now, here is an important remark. Okay. Not the knowledge of Phi-n, the Euler-Tolschian function, okay, is equivalent to knowledge of factorization. Let's just take a look. So let's see if we can factorize n to get PQ. Obviously, we can obtain Phi-n because Phi-n can be derived from this formula. Okay. The important thing is the other direction is also true. So if you know Phi-n directly, and then that bit of information can be used to calculate P and Q, to factorize P and Q. Let's take a look. So first, we already have a relationship. N is equal to PQ, but we don't know what P and Q are, but we know that N is a multiple of P and Q. So that's a relation. And here, this Phi-n establishes another relation for P and Q. So you actually have two relations, and then you have two unknowns, P and Q. So you have a set of simultaneous equations of two variables, which can be solved. And then it's easy to solve because you can just do simple substitution to get a quadratic equation. Okay, you can eliminate one. You can use one relation to eliminate one variable. okay? And then what remains is a quadratic relation of one variable, which can be solved, okay? So then it is very easy, yeah. So yeah, so very straightforward because we know that P plus Q is equal to N, okay, plus 1 minus Vn, right? So this is the relation. This is the relation, and then P times Q. Yeah. So it's a set of simultaneous equations. So it's very easy. For example, we can use this, and then to substitute P for this N, right? So we substitute P, okay, with N over Q. Okay. So we get a relation, and then there's some Q in the denominator, and then there's a Q here. So we can just multiply Q to get a quadratic relation. So that can be solved. So in other words, this Vn has to be kept secret as well. Yeah. Well, we normally don't regard it as a secret key, but you know, if you just know P and Q, that's enough. Okay. So there's some other remarks. Number one, first, the users of RSA must determine two primes, two large primes, okay, P and Q, and then we choose E, choose a public key to and then calculate the private key. Usually we choose the public key E because this E can be chosen to be small, can be quite small, and then we derive the D based on E. Okay. Nobody does the opposite because there's no advantage of doing that. Okay, and then the prime PQ must not be easily derived from this P and Q. So we know that there are many factorization algorithms that work really well that can be applied to factorize for certain numbers, the numbers of certain format. There are many criteria. This is, for example, like they have to be sufficiently large. Yeah, but I mean, P and Q, when you multiply them together, they're equal to N. So it's possible that P and Q are, one of them is very large, the other is very small because the multiple is is of a fixed size. It's actually better that the P and Q are not too close to each other. And then that means one of them is significantly larger than another, but not too large. Okay, so in other words, one of them is larger, the other is smaller, but they are both very large. Otherwise, there are ways to crack this type of scenarios, and then there are many other things as well. Okay. The security of RSA can be analyzed as follows. There are three things. Number one, we can do brute force key search. This is impossible. The key size is very big, very large. The other is a mathematical attack. For example, like we calculate Vn directly. Okay. The other is timing attack. Use the timestamp. Okay, to get the old key. Now let's take a look at the factorization problem or factoring problem. Okay. To attack RSA, we can do three things. Number one, factorize P, factorize N, and find Vn. Number two, determine Vn directly, if it's possible. Okay, and then once we get Vn, we can use this method, okay, to solve the equation to get P and Q. Number three, find D directly if it is possible. Okay. So far, number two and number three we cannot derive it because nobody has any results on how to do that. Because it involves some mathematics which are beyond our beyond our knowledge. So no mathematicians have any result on this. So even though theoretically there are three ways to do that, practically the only way to attack RSA is number one. Okay, that's because our lack of knowledge. Okay, so far, I mean theoretically, if we can factorize efficiently, then we can compromise RSA theoretically, right? But not vice versa. In other words, if we can reverse RSA, if we can crack RSA, we have no idea whether or not we can do factorization or not. So theoretically, this should be at least harder, right? This is at least as hard as the left side is at least as hard as the right side. It could be harder, but nobody knows. I mean, nobody knows whether or not they are. The level of hardness is the same, or the left side is harder, the right side is a little easier. We don't know. So what should we do? Because mathematicians cannot derive any useful results. then engineers say, okay, it doesn't matter because this is still very useful, right? Well, if we don't have any mathematical results, then we'll just use it. So the situation is currently we believe they are as hard as each other. There's no rigorous mathematical deduction, but you just believe. So you guys may laugh. I mean those people they are not very good at math. So they did things like that, like buggy stuff, right? The theory isn't clean enough. But that's the situation, and then it works. It works. Everybody's using RSA pretty much every day because if you go online and then you use any browser, you'll be using HTTPS, which is SSL, and then within the SSL there's RSA. So you're just using it happily, right, without knowing anything about that. But the thing is, we just believed. We just believe the security is, as hard as doing factorization. Okay. And a lot of mathematicians are working on this. So every year there's some improvements. Okay. And there's some improvements. For example, like there's a quadratic sieve, and there's generalized number field sieve, that kind of thing. Yeah, but they cannot be applied to all cases of n. Okay. Now I will show that if P and Q are too close to each other, then we have there's a trick to factorize P and Q faster than random factorization. Okay. So if P and Q, for example, okay, let's say n is 2048 bits. If you choose P to be 1022 bits, Q is 1022 bits, that's not a good choice because they're just too close to each other. So the best way is one of them is larger. For example, okay, this P is, for example, like 40 bits larger than Q. So your P is 1050 bits, or I mean at least 50, 60, 50 like or 100 bits, something like that. So 1,100 bits for P, and then 900 bits for Q, something like that. So there is a gap between P and Q. Okay, one of them larger. Let's take a look at the reason. If not, there's a tricky way. It's not too hard, but it's a little tricky. We can reorganize n using P and Q. So n is equal to pq. So if you look at these this calculation, we consider p plus q divided by 2. Okay, so p plus q, we have p squared plus q squared plus 2pq. Okay, and then whether it's p plus q or p minus q, we have p squared plus q squared divided by 2. So they actually cancel each other. The remaining term is we have a 2pq here on the left, and then divided by 2. So we have one copy of pq. And then here we have minus pq, right? So you have a pq minus negative pq. That is why you have pq divided by 2. Oh, I'm sorry, this is not divided by 2, divided by 4, because 2 is squared. So it's equal to pq. So in other words, pq can be represented as the difference between two squares. One of them is the same as p plus q. Yeah, it's at the order of p plus q. The other is at the order of p minus q. Okay. Now we introduce two variables. We call this p plus q divided by 2, okay, t. And then p minus q divided by 2 is called s. Okay, we introduce two new variables. So given p and q, we can have s and t. Okay, and they can be and then these two new variables, they can be inverted. In other words, you get t and s, you can calculate pq. So in other words, we find a relationship between this by introducing two new variables, and then one of them is related to p minus q. Now we're taking advantage of this p minus q. If p and q, they're too close to each other, then this p minus q is small. Okay, so we can take advantage of that. When you do when you do brute force exhaustive search, you're working on two parts, right? You just randomly generate p and q. By randomly generating p and q, it's the same as randomly generating t and s. But now we have an advantage, because if s is small, in this case, having the knowledge that s is small, we can actually randomly generate more t's. So taking this advantage, if we randomly generate t and s, it will be faster than randomly generating q, because we have some key information. P and q are close to each other. So as long as you have any information, or as long as you have any relation between variables, when you randomly generate anything, oftentimes we can reduce a problem to something else that's related to a certain type of property, and then for that property you can generate less number of variables, to take advantage of that. So you'll be sooner to find t and s, okay, if you randomly generate ts, okay, as compared to randomly generating p and q. Okay. And there are other things as well. It's not just that. And over these years, it's more than 40 years old, right? It's 45 years old, because RSA is as old as I am. So it's 40 years old. Over these years, mathematicians, engineers, they found some weakness of certain parameters. They satisfy some relation. So every time they found a relation, there will be a new criterion here. Okay, so when you choose you choose p and q, when you choose your parameters, you avoid those criteria. Okay. So the number one is p and q should be too close to each other. Number two, yeah, this is related to another paper, that some other mathematicians found. The p minus 1 and q minus 1 should have a fairly small GCD. So their smallest GCD shouldn't be too big. Otherwise, it's there are other ways you can use. There are other methods you can use to exploit this property to reduce the exhaustive key search. And also others, both should have a fairly small GCD. Okay, for example, like fairly small GCD, and then there are other large prime factors. We know that p minus 1 and q minus 1, the GCD, they at least, they have a common factor too, because p and q must be an odd number. So p minus 1 is an even number. Okay, q minus 1 is also even. So at least they have a common factor too. But if you have a common factor, if other than 2, your next common factor is really big, like 300 bits, that's not good enough. Your GCD is just too big. So your GCD should be fairly small. But each of them should have a really large prime factor. And that's the thing. So you're p minus 1. So p minus 1 and then q minus 1, right? So this is, for example, your GCD is g, is something like that. And then times something. And then you have a really large prime. For example, this is p1 and then a really large p2. And then you have some other things. Okay. So this is prime, this is prime. And then you have other non-prime factors. So you have so this should be small. This is small. And then this is big. You have a large prime. This is a large prime factor. Even though the obviously p minus 1, q minus 1, they're not prime. Okay. So this is better. They have large primes and then small GCD. And then for other non-prime factors, they don't affect anything. So I just listed 3, and then I haven't updated this for a while. Now there are other criteria as well. Yeah, because over these years there are some improvements. Okay, so that's idea. So that's RSA. That's RSA encryption. So I actually didn't post this online. I apologize for that. I will do that as soon as as quickly as possible. Now let's move on to other public key crypto systems. We will focus on 3 of them, and then this type of crypto systems, they're based on a different hard mathematical problem, i.e., it's called the discrete log problem. It's not based on the factorization problem. Oh, I'm sorry. These 2 are based on the discrete log, and then this rapid encryption depends on the factorization problem as well. So let's take a look. So remember when we were introducing the asymmetric crypto systems, I said, in the last lecture we talked about one-way trapdoor functions. Right? So what's one-way trapdoor function? It's a one-way function with a trapdoor. Okay, a trapdoor is some key information. Okay, so that's one-way trapdoor function. And also, it must involve some hard problem. So a hard problem exists because there's one way that if you do the calculation in one way, it's easier. But the opposite is very hard. And then there is significant gap of hardness between the forward and backward direction. Right? The forward backward direction. So the factorization problem, if you guys remember, we know that given P and Q, right, we find N. This is multiplication. So this is multiplication. This is factorization. Right? So this is easy, and then this is hard. So what's RSA? Okay, our RSA is based on this. Okay, this fact. And then what's the trapdoor? Okay, the trapdoor is, when you factor, the trapdoor is you get either P or Q. If you have any piece of some secret information like P or Q, then with the help of P, it's very easy to find Q because you just do a division. So that's a trapdoor. So factorization problem is one of them, and there's another one called discrete log. There's another type. And then these algorithms, they're based on the discrete log. Okay. For factorization, RSA is based on that. Then there's another one called Rabin as well. And then Rabin is different from RSA, but they're uses kind of like similar idea, and then they have different properties as well. There are pros and cons. So it's really difficult to say which one is better. Okay? But the thing is, nobody uses the Rabin. Why? Why? Because this one comes first. It's not because RSA is better, no. So that's why, in the world, in most cases, you just have one, number one takes everything. So in English, there's a saying called winner takes all. Okay, so winner takes all, it doesn't mean you're the best at all times. It only means you're the best at some moment, and then you're the winner, right? And then if you take the market, then it takes all. Okay, so oftentimes it's like that. Actually, there are a lot of them. I mean, like that. For example, like Microsoft. We all know Microsoft sucks, right? But over these years, Microsoft still one of the best, largest software companies because MS-DOS, the DOS, and because of the DOS system, Microsoft kind of got up really strong. But it's after Windows system, after they released the Windows system, they really took the market. Over these years, there are a lot of software companies that want to do something. There's some of them that are really good. For example, like there's like 3D printing software. They're doing really good. And Microsoft also has 3D printing software. But what Microsoft did is that if somebody wrote a better program software, they bought that company, and then they just let that company idle. That's what Microsoft did. So they use this. They buy you up so that there's no competition. So you're bought, right? And then they pay you, and then they just want you to idle. Don't do anything better than Microsoft. That's one of the main reasons why they're still, they still suck, right? Over these years, this software still suck. But that's reality. Winner takes all. Well, so Rabin is competitive as well. I'm not saying Rabin is better than RSA. They're pros and cons. Rabin is kind of a weird algorithm. It's really weird because the encryption is extremely fast, like really fast, but the decryption is slower. So the decryption is like 3 times slower than RSA, but the encryption is more than 10 times faster. So this is kind of like weird algorithm. Anyway, it's so Rabin, because it comes second to RSA, it's not used. And then for this category, discrete log problem-based algorithms, there's Elgamal. This is a really good algorithm. Unfortunately, I personally think this is actually better than RSA. Unfortunately, RSA is the best, so nobody uses Elgamal. Okay, and this elliptic curve. Oh, this one is because this is very different, and then this can be used on portable devices because it's very extremely fast. So there's some people using that because you simply it takes a lot of time to run RSA using cell phones. Probably not now, but at least 10 years ago when I came to NTHU, I led a group of undergrad students implementing elliptic curve and then RSA as well. So this one on cell phone, it took like a few milliseconds for one encryption. For RSA, it took like 1 second or something, 1 or 2 seconds. That is why this is really fast. So there's people using that. And then there's DSA. The DSA The DSA is an improved version of the Algama signature. This is not an encryption algorithm. This is signature only. Okay, so no encryption, no key exchange. It's signature only. This is another competitor of RSA as well. So encryption-wise, RSA, elliptic curve in smaller devices. Key exchange, RSA, and Diffie-Hellman, they are competing with each other, the two alternatives. And signature, RSA and DSA. So that's the situation. That's pretty much the situation. Okay. So, and then these are really important. I mean, the encryption algorithm, these are really important. So those are commercial algorithms, not for military use. For example, right now, the Russians, they actually created their own encryption and communication system called, I think, ERA or something. They spent millions of dollars, millions of rubles to develop an encrypted communication system, which is totally useless, right? Because they're cracked. Yeah. Let's take a look at the rabbit. So rabbit encryption is a weird algorithm, but because of its relation to RSA, we still introduce that. It's extremely fast to do encryption, but decryption is much slower. Okay, it's slower than RSA, about 3 times slower than RSA. So if you have a scenario that a lot of people are doing encryption, then this could be a good choice. Unfortunately, it's not a competitor of RSA because it came later than RSA. Let's take a look at the key generation. Number 1, first we generate 2 primes, P and Q. Okay, that's the same. Okay, and then N is equal to PQ. It's also the same. The public key is N, private key is P and Q, so it's the same. Encryption. Let's just take a look at encryption. So you represent the message as an integer in the range. This is exactly the same as RSA. Let's take a look at the encryption. The encryption is a total surprise. You calculated it's square. That's it. So just square. Okay? That's right. The big surprise. Decryption. So encryption is squaring. What about decryption? Square root, right? But now the problem is we are not working with real numbers. Okay, not even integers. We're working with modular arithmetics. Okay. So modular arithmetics, their properties are not always the same as natural numbers. So sometimes they are close. Sometimes they're very different. So this is a subject that we feel like both familiar and not familiar. 这就是我讲说这个MAD 的这种运算呢，是一个既熟悉，对同学来说是个既熟悉又不熟悉的一个主题。有些东西很像我们一般的这个数字，但是它有一些东西是很不一样的。我们等一下就看一下。我举个例子哈，你这是一个平方的一个东西，对不对？好，你开根号是不是就2个解，一个正负什么嘛，对不对？因为这是个平方的嘛，对不对？所以你就是2次4解就正负。这个平方开出来有4个，很奇怪嘛，对不对？等我介绍一下。Okay, so we're working on this. We're working on something like m squared mod n. Okay, something like that. Okay. This is called modular arithmetic. Because you have this mod. Modular arithmetics. This the behavior of this mod sometimes is really different from ordinary numbers. In this case, the biggest difference is that if you find a square root, okay, you end up with 4 numbers. So this comes at a total surprise. How is that possible that if you do square root, you end up with 4? Let me show you what that's really possible. So let's choose something that's a little easier. For example, let's see. Okay. So let's let n to be, for example, smaller numbers. 3 times 5, okay, that's 15. And then we look at the square root. But the thing is, so far, we still cannot handle anything like solving the equation, okay? We cannot find the square root because we have no knowledge about the square root operation in modular arithmetic because they follow different rules. So we do it the opposite direction. We don't do the square root. We actually, let's just look at the squares, okay? So n is 15, and we look at those numbers from 1 to 14, and then look at their squares. Okay, so with these numbers, so 1, 2, 3, 4. Okay, so this is x, okay, and then square. We just look at its square. Okay, mod 15. Okay, so the square should be okay. 2 square is 4. Okay, 3 square. 4 square is a little different. So 16 mod 15. So this is 1. Okay, this is 25 mod 15. Okay, 25 mod 15. So that's actually 10. Right. 36 mod 15. Okay, so 36 minus 30. So it's 6. Okay. This is 49. Okay. 49 mod 15. Okay. So 49 minus 45. Okay. So this is 4. 8 is 64. 64 minus 60. Okay. 81. Okay. Minus 75. 100 minus 90. 121, that's 1, okay, minus 120. 144, okay, 135, it's about 135. So this is 9, okay. 169 minus 150, no, 165, okay, so it's 4, okay. And then this is 196, okay, 196. Let's see, minus 50, mod 15. Let's see, we can minus this. 180, 180, 190, 195. So this is 1. Okay. Now, so we have a table, okay, so, and then we can look at the table from the reverse version. Okay, so this is their squares. If you look at from here, this is its square root. Okay, so that's a square root. So we look at from a different direction. Now, let's see if I can other chalk. Yeah, we can look at its square root. Let's take a look. So the square root of 1 is 1. Yeah. But the square root of 1 is 1, not just 1. 1, 4, 11, and 14. So there are actually 4 roots. Okay. So 1, 4, 11, 14. So this is the square root of 1. The square root of 2, nothing, right? So there's nothing. Square root of 3, also nothing. Square root 4. We have 2, 7, 8, 13. Okay? 2, 7, 8, 13. So we actually have 4 square roots. And then 5, nothing, right? Nothing. 6 and 9. So we have 6 and 9. Right? 6 and 9. So these are the one that has square roots. 7, nothing. 8, 9, 3 and 13. 3 and 12. 10 is 5 and 10. 5 and 10. 11, nothing. 12, nothing. 13, nothing. 14, nothing. So we have 1, 2, 4, 8, 10, okay, 14. Yeah. So as you see that, some of the many numbers do not have square roots, but some numbers have 4 square roots. Some numbers have 2. Okay. That's because n is equal to a product of 2 primes. Okay. But altogether they're the same. So it's like, in Islamic countries, man can have up to 4 wives, right? So do you think it's a good idea? I mean, if you, as a man, you think it's really good? From a statistical point of view, it's not always good. Because if somebody can have up to 4 wives, that means somebody won't have any wives at all. On average, if you calculate the average of wives per man, it's the same. Men do not have any advantage at all. Let's say if you're born in a rich family, then you can have up to 4 wives. But if we just take, let's see, I mean, you are born in a poor family, then you can't afford wives at all, right? So from a statistical point of view, it's not always good. It looks good, but it's not good. So the same thing here, because some numbers have up to 4 square roots. They took the square roots from others. Altogether, it's the same, right? So no advantage at all. Don't be tricked. So let's continue next time.